This is the third of 4 lectures from Chapter 5 about gases, and I should have had a subtitle here. This one focuses on ideal gases, or the ideal gas law. Before we start calculating using the ideal gas law, which by the way is PV equals nRT, that means pressure times volume of a gas is equal to the number of moles of a gas times R, which we'll define more specifically later. That is called the gas constant, times temperature, of course, which must be in Kelvin, as with all gas laws. So in order to make calculations with this ideal gas law, and as a matter of fact, all of the gas laws, we make some pretty big assumptions about the behavior of gases. And the most important one is that an ideal gas has no interactions between the molecules. That means there are no attractive forces and no repulsive forces. That assumption's pretty valid under most conditions because gas molecules are so far apart from one another. That assumption about no interactions is especially holds true under the conditions of low pressure and high temperature. So I want you to think on a molecular level. When you have a low pressure, what do those gas molecules look like? They're really spread out, okay? They're really spread out, and so they're really going to behave ideal. Same thing with high temperatures. High temperatures also cause the molecules to spread apart, and therefore they're not feeling interactions between one another. You will see the gas constant designated as a capital R in the ideal gas law, and you'll see it off and on again throughout chemistry. So you need to commit to memory the two values that we use most frequently. Now, the gas constant is a constant, but there are all sorts of different units that it's used in depending on the units of the other variables in your equation. So by far what we'll be focusing on most in here is the gas constant with the units liters, atmosphere, moles, and Kelvin. That is 0.08206. And what you need to be very careful when you're doing calculations is that the units of your other properties match these units. So in other words, volume has to be in liters, pressure has to be in atmosphere, and of course moles, and temperature has to be in Kelvin in order for this R value to be appropriate. So here's an example using the ideal gas law. If you're pretty comfortable using algebra, and go ahead and try it yourself, otherwise I will work through it for you. So let's go ahead and fill these variables in as we get. So there's volume, okay? Here's moles and pressure, and it's asking us to solve for temperature. So let's plug in what we know. It's pretty straightforward. 1.85 atmosphere times 47.3 liters. Now pay attention to the units. That's probably the most common thing that can trick you up. So far the units are correct. They match the universal gas constant units. Okay, we have 1.62 moles. The universal gas constant is 0.0821, and we're asked to solve for T. So all these equations, what you're solving for, you need to isolate. We need to isolate temperature. That means we need to divide both sides by 1.62 times 0.0821. So let me go ahead and rearrange this. This is what we have so far. And the heavy breathing is my dog in the background. Okay. All right. And so you go ahead and plug that into your calculator, and you will get the temperature. Remember, you're going to get the temperature in Kelvin, not Celsius, okay? and that gives us a temperature 658 Kelvin. So if a problem asks you to express temperature in Celsius, which a lot will, remember Kelvin's always a larger number. In this case, if you're going from Kelvin to Celsius, you need to subtract 273. We are going to start carrying out stoichiometry problems using gases, and so there's a new conversion factor we need to know. The conversion factors we've learned so far is that 1 mole, if we're talking about particles, we use Avogadro's number, 6.02 times 10 to the 23rd. That would be molecules, right, or atoms or something. If we're talking about molar mass, or excuse me, if we're talking about grams, then 1 mole equals the molar mass of the substance. Okay, so that's when we're talking about grams. And now our new conversion factor is that if we're talking about gases, and they have to be gases at standard temperature and pressure conditions, 1 mole of any gas at standard temperature pressure conditions is 22.4 liters. Okay, so make a note of that. It's something you need to commit to memory. And as kind of a side note, the density of a gas, okay? So density always is mass over volume. The units usually used when you're dealing with a gas is grams per liter. Now, there are longer ways to calculate density, but if you happen to remember this handy-dandy formula, it makes life so much easier. So density would be the molar mass of a gas divided by its molar volume. Let me show you an example so you can see how easy this is. So again, it's before you use this 22.4 liters per mole, you have to be at STP conditions, so be careful with that. Let's say that I asked you what the density of helium is or the density of nitrogen at STP conditions. So remember the formula. Density is the molar mass of the gas, that's from the periodic table, divided by the molar volume. Okay, and as long as you're STP, the molar volume is 22.4 liters per mole. So the molar mass of helium is 4. Just look at the periodic table. And we're at STP, so molar volume is 22.4. Notice that the moles cancel, and so you've got the density units you want for your gas. And doing the same for nitrogen. Nitrogen is a diatomic, so molar mass is 28. It's a STP condition, so molar volume is 22.4, and so the density of nitrogen gas, 1.25. So there are some longer ways to calculate density, which you'll see later on, but this formula just makes it very, very easy. So here's the longer way to do it. If you look at the ideal gas law, if you don't memorize the formula for density, you look at the ideal gas law, and if you rearrange it so that it looks like this, we actually have density, right? N is moles. Volume is liters. Moles over liters is kind of like density. Really, density is grams over liters, but we know how to get from moles to grams. So you can rearrange the ideal gas equation to be pressure divided by R over T, and that would also lead you to density. This form of the equation is important because we can get additional information from it. Please don't get overwhelmed by this slide. I'm not going to make you derive this formula. What this whole slide is leaning toward is I want you to be able to solve for molar mass. I'm not going to make you go through this. You're welcome to look it over if you want. But basically, if we rearrange the ideal gas equation to look like the density form that I showed you on the back last page, and then we realize that the number of moles, how do we get moles usually? We get it by taking mass, grams, right, and dividing by molar mass. That's usually how we calculate moles. So I simply, instead of putting N for moles, substituted mass divided by molar mass. The reason I did that is because there's a cool formula which you need to commit to memory on the next page that allows us to determine the molar mass of any gas we analyze. So let's look at that formula. And here we go. If we do the derivation that I just showed you on the previous page, which again I won't make you do, and we rearrange, we can solve for molar mass of any gas. What does it equal? It equals to the density of that gas, so you need to know the density, the gas constant times temperature in Kelvin divided by pressure. So here's how I always remembered this formula, in case it helps you, because you probably have noticed there are a lot of gas law formulas. How I remembered it is I said mangy mutts, MM, put dirt, okay, DRT, dirt, over their P. Mangy mutts put dirt over P, over their P. I don't know if they do or not, but that's how I always remembered that formula. So here's another example for calculating, and if you see molecular weight, that means the same thing as molar mass, just so it doesn't throw you off. So go ahead and see if you can solve this problem on your own, okay? And I'll give it to you again here. Mangy mutts put dirt over their P, and I want you to see if you can solve for molar mass, and then check in on the next page and see if you got it right. Let's take a look and see if we have all of the variables we need and if they're all in the right units. None of these gas laws are complicated, mathematically speaking, but there are all sorts of little tricks. The most important is units. So let's look. We have pressure, and it's in atmospheres. The R value that we're almost always going to use is 0.0821, and the units are liters, atmosphere over mole, Kelvin. So all of our other variables have to have these units. So pressure's in atmospheres like it should be. Here's volume. Okay, it has liters like it should. Here's a problem. Our temperature's in Celsius. So let's go ahead and find out what the temperature is in Kelvin. 288 Kelvin, and that's the value we're going to have to plug into the formula. They gave us density, grams per liter. That is the correct units for density in order to get molar mass. And here's the answer. Plugging everything in, we find that the molar mass is, let's see, 32.3. Remember, units for molar mass are grams over mole. And do you think you can guess what this gas might be? What gas, really common gas, do we know that has a molar mass of 32? Oxygen. So that's it for ideal gas law. I'm hoping that you have gone to the problem solving folder and begun to work as many problems as possible. If not, now is the time to do so.